time for a new chapter. Today we start chapter 15, and we're moving on to the second major topic for the semester, equilibrium. Remember last chapter we were talking about kinetics and talking about how fast we get to a chemical reaction. So we talked about looking at the slope of our concentration versus time graph. But what I want you to notice this time about the concentration versus time graph is that we reach a point in time where the graphs flatten out, where the concentration of the reactants and products stop changing. At the point in a reaction where the concentrations of reactants and products stop changing, we've reached what's called equilibrium. Scroll up for me. So, when we reach the equilibrium point, okay, we've reached a constant concentration of reactants and products, but the reaction in the beaker is not static, it's dynamic, which means that although the concentrations have stopped changing, the forward reaction and the reverse reaction are still going on. It's just that at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. Remember last chapter when we were looking at elementary steps and we were talking about reaction mechanisms, we talked about the fast step coming to equilibrium, waiting for the slow step to happen if the slow step was the second step. Okay, so let's define equilibrium. There are two ways to define equilibrium. We can say it's the point in a chemical reaction where the concentrations of reactants and products stop changing. That means the reaction seems to have stopped. Okay, and this is the original definition of equilibrium based on experimental experience. The second definition is that it's the point in a chemical reaction where the rate of the forward reaction and the rate of the reverse reaction equal each other. Because they equal each other, there's no net movement of material between the reactant and product side. For everything that goes toward reactant, there's something to balance it out coming back from product to reactant. This second definition, okay, depends on our knowledge of kinetics. And the mathematics of equilibrium chemistry was worked out experimentally long before we understood kinetics. But we're going to start out here in this chapter because we've already been through kinetics, kind of looking at this from a kinetics point of view, rate of forward reaction, rate of reverse reaction, okay? And then kind of progress from there. So let's scroll up here a little bit. We're going to look at a really simple reaction, okay? Now, let's scoot over here. Make sure we got a good shot at the, yeah. We look at a simple reaction, okay? N2O4 going to two NO2s. Everything's in the gas phase. All right? Now, this is an elementary step. Now remember, an elementary step means that this happens as a single event, okay, instead of a cascade of events. And we know for a single event, we can write the rate law based on the coefficients in the balanced chemical equation. So the rate, subscript F for forward, equals little k forward, the rate constant, times the concentration at N2O4. The rate reverse is equal to Kr times the concentration of NO2 squared. Now, at equilibrium, rate forward is going to equal rate reverse. So I can say that Kf into O4 equals K reverse NO2 concentration squared. Now, if we play with this mathematically a little bit, I can get something interesting. I divide both sides by Kr, so I get Kf over Kr times the concentration of N2O4 equals the concentration of NO2 squared. And I'm going to put little EQ here behind the two concentrations because we're talking about equilibrium concentrations. Now I'm going to divide through by N2O4. Now I'm going to write it, well, I'll just write it down here. If I do that, I get Kf over Kr is equal to NO2 concentration at equilibrium squared over N2O4 concentration at equilibrium. Okay, why did I do all that? Well, if I take a constant divided by a constant, I get a new constant. So that tells me that the concentration of nitrogen dioxide relative to the concentration of dinitrogen tetraoxide at equilibrium is a set ratio, okay? This is equal to a big K, which we call the equilibrium constant. So that at equilibrium, there is a fixed relationship between the concentration of products and the concentration of reactants. Now, I want to remind you that Kf, little kf and little kr, the rate constants are temperature dependent. So that tells me that the equilibrium constant is also going to be temperature dependent. But as long as I'm holding the temperature constant for a reaction, there is a set ratio here. And notice it's a ratio. I don't have to reach specific concentrations, just the ratio between them have to be balanced. Okay, scroll up for me. Okay? So, keep going. Let's talk a little bit about K, equilibrium, and what it tells us. Now, looking at the equilibrium constant, the size of the equilibrium constant is going to tell us something about how much product we're going to get relative to how much reactant. If KQ, the equilibrium constant, is greater than 1,000, then that means that we're going to have about 1,000 times more product than we do reactant. So large values of K indicate that the forward reaction is favored and there's going to be lots of product at equilibrium and very little reactant at equilibrium. If we do the flip side, where K is small, less than 1 times 10 to the minus 3. So you have 1,000 times more reactant than you do product at equilibrium. You have a lot of reactant at equilibrium and very little product. This means the reverse reaction is favored. Okay? Values in between those two extremes means that we have a real soup at equilibrium. Reasonable amounts of reactant and product, and neither direction is that favored. Okay, so you got a real mix. Now, what we've looked at so far has been an elementary step. And we know elementary steps are fairly easy to deal with. The next thing we want to do is, can we take this concept of equilibrium from an elementary step and apply it to an overall reaction, which we know on the atomic level is made up of multiple elementary steps. And of course, there wouldn't be a chapter if the answer was no. The answer is yes. Okay? And we have the law of mass action. The law of mass action, which was worked out experimentally, says that at a given temperature, a chemical system will reach a point at which the ratio of product concentrations and reactant concentrations reach a constant value. The rational expression is based on the coefficients in the balanced chemical equation. This rational expression is called the equilibrium expression and appears as follows. So scroll up. Okay? For any reaction, little a of A plus little b of B going to little c of C, little d of D, the equilibrium expression is the concentration of C at equilibrium to the little c, concentration of D at equilibrium to the little d, concentration of A at equilibrium to the little a, concentration of B at equilibrium to the little b. So I can look at any balanced chemical equation and I can write its equilibrium expression. So let's look at a couple and let's write out the expression. Okay? Now we've got the reaction. 2 sulfur dioxides in the gas phase plus an oxygen in the gas phase, going to 2 sulfur trioxides in the gas phase. So let's look at writing the equilibrium expression. If I write the equilibrium expression, KEQ, now your book doesn't use the EQ, but I'm trying to reinforce the fact that it's equilibrium. I'm going to have the concentration of sulfur trioxide at equilibrium squared over the concentration of sulfur dioxide at equilibrium squared times the concentration of oxygen at equilibrium. The powers are the coefficients in the balanced chemical equation. Okay? The other reaction that I have here as an example for you guys to look at, okay, make sure you got it, is the reaction between nitrogen, gas, plus hydrogen in the gas phase going to ammonia in the gas phase. Okay, so 1 nitrogen reacts with 3 hydrogens to give me 2 ammonias. So the equilibrium expression here is going to be ammonia concentration squared over the concentration of nitrogen times the concentration of hydrogen cubed, and these are all equilibrium concentrations. Okay? Now, related to the equilibrium concentration is something called the reaction quotient. Now, the reaction quotient is algebraically the same as the equilibrium expression. Okay? The only difference is that for the equilibrium expression, all of the concentrations must be equilibrium concentrations. For Q, the reaction quotient, you can be at any point in the reaction. You don't have to be at the equilibrium point. So Q looks algebraically the same as K. Except the concentrations are equilibrium concentrations. You could say that the equilibrium expression is just one solution, the important solution of Q, the one that happens when the concentrations are equilibrium concentrations. Now, let's scoot back over and look at our screen. All right, so we can say that Q equals the equilibrium constant if we are at equilibrium. So comparing Q to K will help us determine if a reaction is at equilibrium. So if you know the value of K, you know the concentration of the reactants and products, you can calculate a Q and you can compare. If Q is less than the equilibrium constant, we're not at equilibrium, and the reaction must run in the forward direction to get there. We have too much reactant compared to product because Q is too small. That means the denominator is too small. Scroll up. If Q is greater than K, the reaction is still not at equilibrium, but this time it has to run in reverse to get to equilibrium. There's too much product compared to reactant. I've got a number that's too big. The numerator is too large compared to the denominator. So if we know what concentrations are in a reaction vessel, and we know the value of the equilibrium constant, we can determine if the reaction has reached equilibrium or not, and we can determine what direction the reaction must quote-unquote run to reach equilibrium. So we're going to look at problem 15.7 on page 655 in your textbook. Okay, let me read it to you. The problem says, consider the reaction and its equilibrium constant. So let's scoot over here. I am going to work problem. Let me get the board clean. All right, we're given the following. We're given a nice simple reaction into O4 gas going to NO2 gas, and there's 2 of those. And we're given the equilibrium constant here, K, as being 5.85 times 10 to the minus 3. Now notice they put a little c down as a subscript for the K. C says that the equilibrium constant is going to be written in terms of concentration. we're told that right now the concentration of NO2 is 0.0331 molar. The concentration of N2O4 is given as 0.0225 molar. And it asks, are we at equilibrium? And if not, what direction does it have to proceed? So what we have to do is we have to write our Q expression. Q is going to be the concentration of NO2 squared over the concentration of N2O4. So in this case, it's 0.0331 molar squared over the concentration of N2O4 to the first power. So let's plug that in and get our answer. Where did I lay my calculator? And I do not see it. Okay. Now I've got my phone. I'll just pop it in real quick. So let me use my phone. Not the ideal situation, guys. Don't do this on a test. I will start laughing at you and hand you a calculator. So let's do it. 0.0311. Oh, excuse me, clear. 331. I didn't write the number in there. I just wrote the symbol again. It's 0.0255. So I get an answer here of 0.0430. Now let's compare that. I'm going to write it in scientific notation. That's 4.30 times 10 to the minus 2. So if I compare Q to K, Q is 4.30 times 10 to the minus 2. K is 5.83 times 10 to the minus 3. I can see that Q is greater than K. So I'm not at equilibrium, and because Q is greater than K, this sucker is going to run in reverse to reach equilibrium. Okay, so there's a simple equilibrium problem. All right, so let me erase, and we'll move on to the next thing. Now, while I'm erasing, the next thing we're going to look at is how to use information that's already done, experiments that have already been run and cataloged. Okay, at this point, what we're going to talk about, okay, is how to use reactions where we already know what the equilibrium constant value is to predict what the equilibrium constant value is going to be for a new reaction. So, if we start looking at things that we can do, one of the things that we might want to do with a reaction is look at the reverse reaction, just flipping the reaction around. So if I have A plus B going to C, and I know what the equilibrium constant value is, I can use it to determine what the equilibrium constant value is for C going to A plus B. Now let's look at the equilibrium expressions. Equilibrium expression 1 is C divided by A times B. Equilibrium expression 2 is A times B over C. Hopefully you'll see that they're inverses of each other. So what I can say is equilibrium constant 2 is 1 over equilibrium constant 1. So if equilibrium constant 1 is 4, equilibrium constant 2 should be 1 over 4. See? Or 0.25. Now, if we might ask me, why in heaven's name would I ever want to do that? Well, sometimes we're going to look at how we combine reactions together to get a new reaction. Okay, think about multiple steps. And I might have to reverse a reaction when I'm getting ready to add it in. So that's one of the reasons we'd want to do something like that. Now, let's look at multiplying by a coefficient. So if I have A plus B going to C, and my reaction 2 is 2A plus 2B going to 2C, if I compare their equilibrium constants, what I hope you see is that equilibrium constant 1 squared gives me equilibrium constant 2, because C is squared, A is squared, B is squared over here. So if equilibrium constant 1 is 4, equilibrium constant 2 would be 4 squared, or 16. Okay, again, if we're looking at ultimately being able to combine different reactions together to create a new reaction, we might have to multiply through by a coefficient. Okay, scroll up. Now, what we've been leading to then is talking about adding 2 or more reactions together to get an overall reaction and a new equilibrium constant for that overall reaction. So if I had A plus B going to 2C, and I added to it a reaction 2C going to D, if I look at their equilibrium constants, okay, C squared over A times B, B over C squared, there are their numbers, scroll up for me. If I add the 2 reactions, not that far, just bring it down, just perfect, thank you. If I add the 2 together, the reactions, I get A plus B goes to D, with the equilibrium constant D over A plus B. If we look at combining these 2 together somehow to get the bottom one, what we notice is that if you multiply these 2 together, you get this, okay? So that means our equilibrium constant 3 is equal to the equilibrium constant 1 times equilibrium constant 2. So in this case, 6 times 2 would give me 12, which is cool. So we're going to look at practice problem 15.2 on page 647. Okay, so let's look at the practice problem. Now, if we look at the practice problem, we are given the following reactions. Okay, we're given 2 carbon monoxide difluorides, gas, plus decomposing into carbon dioxide, gas, and carbon tetrafluoride, gas. And the equilibrium constant here is 2.2 times 10 to the 6. Okay? We're asked about the following reaction. 2 carbon dioxides plus 2 carbon tetrafluorides decomposing into combining to give me 4 carbon monoxide difluorides. Yeah. Now, I want to compare these 2 reactions. One of the things that I noticed about these 2 reactions is that carbon dioxide is a product here and it's a reactant here. So I know one of the things I did is I flipped the reaction. So I'm going to take this one and I'm going to flip it. So carbon monoxide plus carbon tetrafluoride going to 2 carbon monoxide difluorides. The equilibrium constant here is just going to be 1